Good day, I'm Norman Wildberger. We're in the process of having an re-evaluation of the Algebra of Boole and the relation with Boolean algebra and logic. So with George Boole, we enter a new phase where Boole takes classical logic from philosophy, originally motivated by Aristotle, and models the essential aspect of that into mathematics. This is a huge new development which ends up having major consequences for 20th century computing. So today we're going to investigate this thing further, and I want to point out that there are these important relations. First of all, the characteristic 2 relation, the fact that when you take x plus x from this field, you necessarily get 0. That has the consequence that that also holds in this algebra. So you take any vector and you add it to itself, you get the 0 vector. That's an important consequence. Another important property that Boole identified is this idempotent law, that for any one of the two elements in the Boole field, or the Boole bifield, x squared equals x. So 0 squared equals 0, and 1 squared equals 1. That kind of relation is called an idempotent law, when the square of something is equal to itself. And it turns out, just because this is component-wise, that it's also valid in any of these Boole algebras. You take any vector and you square it. All its entries are either 0 or 1, so at every component this rule is applying. So you square the entire vector, you're going to get the vector back again. All right, so this is an important additional property of the Boole algebra. Okay, so today we're going to investigate a little bit more the structure of these algebras, and then we're going to apply things to Aristotelian syllogisms. And we're basically going to trace the footsteps of Boole in recasting this classical logic now purely in terms of algebra. And you'll see that the algebra is quite simple. And I should note that this approach that I'm showing you now is not standard. So most people these days have forgotten about the algebra of Boole, and they're actually doing something different, which is Boolean algebra, which we're going to talk about later, but we're going to see that as somewhat secondary. Okay? It's the Boole algebra itself, which I want you to think about as being primary. That's the original algebra that Boole set out. So to get us thinking in the right direction about Boole algebra, let's have a look at this example that I talked about in the previous video, where we were looking at a population of 5 beings and various properties on that population. And I remind you the properties were like being human, being athletic, being noble, and I had a few others. Let's just look at these 3 properties here. So the human property, we have 5 things. And the first 4 have the property h. Now, originally we said that was the property of being human, but we actually don't really care about the actual nature of the property. We just say that there's a property h and it's satisfied by the first 4 but not by the others. Okay? So it's represented by this Boole vector in our 5-dimensional Boole algebra. Now, let's have a look at what we can do with these 3 vectors which are in this 5-dimensional Boole space. And maybe I should remind you that the number of Boole vectors in total in this space is 2 to the 5th, or 32. So it's a very finite situation. We have 32 vectors and we've chosen 3 of them. So the first thing that we might think about doing is looking at the subspace spanned by them. So we're thinking of this as a vector space, admittedly in this bifield aspect, but it's still like a vector space. So we can take linear combinations of these 3 vectors. So what happens if we do that? If we take h plus a, we add them component-wise using the bifield operation, so that's like mod 2 arithmetic. Then the 1 plus 1 is the 0 there, and then we get a 1, and then we get another 0, and then a 1, and then 0. So the sum is 0, 1, 0, 1, 0. That's a new vector. If we add h plus n, we get a 1, and then a 0, a 1, 1, 1. So we get that vector there. And if we add a and n, we get 1, 1, 1, 0, 1. And I guess we can also add all three of them together. H plus A plus N. So that'd be like taking that one and adding N. And then the ones there would disappear. We would just get 0, 0, 0, 1, and a 1. So we can picture those vectors in this diagram here. So it's like a cube, and there's the 0 vector, okay, which is also in the span because it's 0 times any of these vectors. So that's this vector that's all zeros. And then we have H right there, and we have A right there, and we have N right there. We're thinking of this as being like in a three-dimensional space. But if we go in this direction, there's only one vector in this direction. Starting at 0 and then go H. If you take H plus H, you get back to 0. There's nothing else in this direction. In any of these directions, there's always only two vectors. Okay, and then there's the various sums that we've created. So there's H plus A, there's H plus N, and there's A plus N, and there's the sum of all of them, H plus A plus N. And they form a three-dimensional subspace. So it's the span of H, A, and N. We might use that vector space terminology. So geometrically, that forms a cube. So there is some geometry here, but it's a kind of bifield geometry. Since our Boole algebra actually has a multiplication as well, if we start with these three vectors, it makes sense to ask not just about their span, but also about the algebra generated by them. What are all the possible products that we can get as well as sums? So we get a larger space. And what do we actually get? Well, if we take some products, just to get started, if we take H times A, remember the product is component-wise, so it's 1, 0, 1, 0, 0, we get just A back itself. That's actually telling us that there's a relation, a logical relation between these, that this property is sort of contained in this property here. If we do, say, H times N, we would get 0, 1, 0, 0, 0. We get a new vector, which we might call K. It's not in the span. So there's the span. Now we get a new vector that we obtain by multiplication. How about A times N? A times N, we do the product there, we get 0 vector. If we do H times H plus A, there's H times H plus A, we get 0, 1, 0, 1, 0. We get H plus A back again. Okay, here are a few more. You can check. These are just some of the ones that you can get. So you can go through and sort of see what you get. And it turns out that you end up getting a four-dimensional subspace of our five-dimensional space. So there's the original span of H, A, and N. And then here are the vectors that are obtained. It turns out that you're getting all of these together with the vectors that you get by adding K to each one. So for example, this one here, H times H plus N, was this vector here. It's the same as H plus K. Okay. So we get K, we get H plus K, we get A plus K, we get H plus A plus K, N plus K, H plus N plus K, A plus N plus K, and H plus A plus N plus K. And we can think about this as being another cube, and these two cubes are connected also by lines. And so this is really a hypercube. It's a picture of a four-dimensional cube, okay, with altogether 16 elements. So this is like a four-dimensional subspace of this five-dimensional space. And you can check that it's also describable in this way, that it's the set of all 5 tuples, B1, B2, B3, B4, B5, satisfying the condition that B1 equals B3, that the first and third entries are all the same. And you can see that that's sort of reasonable because that's a property that the first 3 vectors had, and that property is going to be maintained under addition and multiplication. So that's a sort of a fast proof to see that you're not getting the entire space, you're only getting this four-dimensional subspace. Okay, so why did Boole invent this nice algebra? He invented it in order to understand the Aristotelian syllogisms and to mathematize that aspect of philosophy. And he was very successful at that. So let's see how that happens. So I remind you of the various four components or forms that Aristotle introduces. So the first general form is every Q is a P. Okay, so we have these two properties, and every thing that has a property Q has property P. That's the first statement, and there's an A here to represent that. And now Boole says, okay, instead of thinking about the properties, let's think about the corresponding Boole vectors. If every athlete is human, that's really encoded by the algebraic relation that the product of the two corresponding vectors, athlete and human vectors, the A times the H, actually is A. Okay, so this is an algebraic understanding of this relation. Now, in the Boole algebra, we can, if we want to, bring everything to one side. So we can add Q to both sides. That's how we do it here. We don't subtract Q, we just add another Q. If we add Q to the right-hand side, we get the 0 vector. And then on the left, we'll get QP plus Q. And then the Q can factor out because of the distributive law. And we get Q times 1 plus P equals 0. So this is another way of expressing this first form. The second form, no Q is a P. That's expressed by QP equals 0. So that would be like if you had, in terms of these things, suppose that you had the property, there's the human property, and you had this property, okay? Those are two properties. And in this case, this is maybe Q and this is P, so no Q is a P. That's represented by the fact that if you take the product of these two things, you can get 0, 0, 0, 0, 0. Okay? The product of the two vectors is 0. Some Q is a P. This is PIQ as opposed to PEQ. Some Q is a P. That's really sometimes the opposite of this one. This one's QP equals 0. This is QP is not equal to 0. No Q is a P. Some Q is a P. It means when you multiply the corresponding things, you're going to get a 1 at least in one place. So there's something that has both the Q and the P property. And the final one, the O property, POQ, some Q is not a P. Some Q is not a P. Well, that's sort of the opposite of this one. Every Q is a P. That's Q times 1 plus P equals 0. Some Q is not a P. That's represented by Q times 1 plus P does not equal 0. So the four forms of Aristotle end up amounting to these four relations between essentially Q and P, the product Q and P, and the product Q and 1 plus P. Now these four fundamental forms of Aristotle can be pleasantly put into a square, and this has been done by logicians for a long time, probably maybe goes back to Aristotle. So it's sometimes called the square of opposition because it interrelates these four forms. So here they are again in the square. So every Q is a P, or PAQ. No Q is a P, or PEQ. Some Q is a P, PIQ, or some Q is not a P, POQ. And now we have the corresponding algebraic versions of these. Q times 1 plus P equals 0, Q times P equals 0, Q times P does not equal 0, and Q times 1 plus P does not equal 0. And now we can sort of see some of the relations. We see that these two here are, well, what sometimes called contradictory. Spell that correctly. Contradictory. Okay, so Q times 1 plus P equals 0. Q times 1 plus P does not equal 0. Those are mutually exclusive, either this or this. Okay, they're not both going to happen. And similarly, the relationship between no Q is a P and some Q is a P, again, those are mutually exclusive possibilities. Either the product equals 0 or it doesn't. There's also some relations in this direction, and the logicians call this contrary and subcontrary. So every Q is a P, no Q is a P. It's also a kind of opposite, but it's not exactly the same kind of opposite as this one, okay? So q times 1 plus p equals 0 versus q times p equals 0. Because p and 1 plus p are, those are the complements of each other, sort of set theoretically. Okay, so throughout, we now have these q and p, the little q's and p's are what we're going to be using here to denote the Boole vectors describing properties or types on a population. And maybe capital P and capital Q are the classical predicates that might be coming from logic in the same context. Okay, so we'll just use this convention that the little q's and little p's tell us that we're working in the Boole algebra. We're talking about vectors with zeros and ones. So we've abstracted whatever philosophical meaning we originally had, and now we're just talking about vectors with zeros and ones and the algebra of Boole that we can do with them. All right, so now we can have a lot of fun because we can go back to Aristotle's syllogisms and we can prove them. Prove them in this purely mathematical context. So we've taken the philosophical stuff, we've extracted what we consider the mathematical essence, we've modeled the philosophy with these Boole vectors, and we've determined that the logistic relations of Aristotle can now be expressed purely algebraically, so we can actually prove the results of Aristotle, and they then become theorems or propositions or formulas. So I'm giving you a somewhat slightly different version than Boole did because, well, I just prefer to do things a little bit more concisely, perhaps. But it's really essentially the ideas of Boole, just recast a little bit in modern form. And I don't claim that this is original. I presume that many people have probably done this or thought about it. Okay, but in any case, I think it definitely deserves to be popularized. Okay, I think we need to reevaluate Boole's understanding here. Okay, so let's start with Barbara. Let's have a good look at Barbara. Okay, Barbara says A little a b, b little a c implies a little a c. So if every b is an a and if every c is a b, then every c is an a. Okay, so let's first of all translate these things here into our Boole language. So the first one, every b is an a. In terms of the corresponding Boole vectors, little a, little b, little c, and so on, the first one is b times 1 plus a equals 0. And that's equivalent to b equals ba. So if we take this thing and expand it out, okay, we saw this is the same as this thing here. This is the Leibniz form, if we like. This actually goes back to Leibniz. Okay, that's sort of compact, that's a Leibniz form. They're both useful. And the second premise here, every c is a b. That's c times 1 plus b equals 0, or c equals c times b. These are the premises. These are the things that we're assuming, and we're trying to establish this one. Okay, so let's do it. So we're trying to establish this. That would be like c equals c times a. We'd like to see that c equals c times a. So let's start with c. What do we know about c? Well, about the only thing we can know is that it's equal to c times b. So we're going to use that one there. There's c times b. Now what we could do, well, we have used that one, so we haven't used this one before, so let's use that. Let's replace the b with b times a. Now what could we do? Well, we've used the two premises. Let's manipulate this stuff here. Let's use the associative law to rewrite this as cb times a. What do we know about cb? Well, that's equal to c. So we get ca. And that's what we wanted. We now have shown that c equals ca. There it is. Or if we wanted, we could recast it this way. It's the same as c times 1 plus a equals 0. In other words, we've proven that every c is an a. So there's our conclusion. So we've interpreted the premises algebraically, we've done a bit of algebra in the Boole algebra, and we've gotten our conclusion. Now you might say, well, which Boole algebra are we working in? Are we working in b2 to the 5th? Yeah, maybe. Or maybe we're working in b2 to the 100, or or b2 to the 10 trillion. Okay, the algebra that we're using applies to all of them, so it doesn't matter which one we're in. So this is a kind of a universal argument that really works no matter which situation that we're in. So this is like a mathematical proof of Barbara using the Boole algebra. All right, so let's go through the others in the first figure. The next one is Celarent. No B is an A, every C is a B implies no C is an A. Okay, so let's interpret the premises algebraically. No B is an A. That's little a times little b equals 0. Every C is a B. That's C equals C times B. So you have to have memorized the relation between the four forms and the four algebraic equivalents. So those are the premises. Okay, so now what we want to do is we want to establish some relation between A and C. We want to show that no C is an A. So let's look at AC. We'd like to show that that's equal to 0. That's what that means. Okay, so AC, what do we do with that? We replace the C with CB. There we go. And now what are we doing? Well, we're using the commutativity there to replace the CB with BC. And then we're using the associativity to replace this with AB times C. But now the AB is 0. So that becomes 0 times C, which is 0. That's what we want to prove. Dari, which is every B is an A. Some C is a B. Implies some C is an A. Okay, every B is an A. That's B equals BA. Some C is a B. That's B times C is not equal to 0. Okay, those are our premises. And we'd like to show that C times A is not equal to 0. Okay, so we're going to be a little bit more sophisticated here. So if we just write down A times C, we can't immediately do anything. So what we do is we write down B times AC. Okay, B times AC. And then we rewrite that as BA times C. And the BA is equal to B. There we go. So that's BC. And then this one tells us that that's not equal to 0. So we've established that the product of B and AC is not equal to 0. And now we use a crucial property of the Boole algebra, that if you have two vectors that multiply to something which is not 0, then both of the vectors must be non-zero. Right? Like if you have two numbers and the product of two numbers is non-zero, then you can conclude that both of the two numbers are non-zero. That works in the Boole algebra just as it does with ordinary numbers. So what we're after here is concluding that this component, AC, has to be non-zero. And that's exactly some C is an A. How about Ferio? So no B is an A, some C is a B, implies some C is not an A, AOC. Okay, so what are the assumptions? So here we go. From A, B equals 0. How do we know that? That's this one here. A, B equals 0. And what is this one? Some C is a B. That's BC is not equal to 0. So we want to have something now about C and A. Okay, so we're going to be a little bit fancier here. So here's what we want. We want to do something with relating C and A. So let's consider B times C times 1 plus A. Okay, let's just consider that. Well, by distributive law, this is like B times C plus CA. Okay, then that's B times C plus B times CA. And I haven't put brackets here because we know by now that everything's associative. Okay, so what do we know about this BCA? Well, we can rewrite it because of commutativity as C times BA. When we do that, what do we have? Well, the BA or the AB is 0. So this term is 0. We just get BC left over. And the other premise is that that is not 0. Okay, so we have this original thing is not 0, and we've used both premises. So what can we conclude? Well, we can conclude that both the constituents here, namely b and c times 1 plus a, have to be non-zero. But what we're really after is c times 1 plus a is not 0. And that's exactly what we need to say that some c is not an a, or AOC. Isn't it pretty? Everything just sort of fits together. It's something that high school students, I think, would appreciate. Maybe high school students should learn this algebra. Why not? It's useful, great historical significance, and as we'll see, lots of connections with modern technology. Okay, but that's only the first figure. We need to go further. So the second figure syllogisms are ones like this, where the first entry, as we read from left to right, are common in all of them. Okay, so I'm going to use the terminology from Wikipedia here so that you can connect easily and sort of check these syllogisms. So if you look up syllogisms in Wikipedia, you will find them listed in the form I've given you here. So the next one is Camestres, which is MAN, and MEX implies NEX. Okay, so the assumptions. Every n is an m, so that's little n equals n times m. And MEX is m times x equals 0. Okay, so we're now after n times x here. So let's look at n times x. So what can we say? Well, the n can be replaced with nm. And then we can rearrange using associativity to get n times mx. The mx is 0, so obviously we get 0. That's a piece of cake. Celarent. MEN and MAX implies NEX. So the first one is MN equals 0, and the second one is X equals XM. Okay, so using those we have 0 equals X times MN. Why is that? Well, because MN is 0. So yes, 0 equals X times MN. By associativity, that's XM times N. But XM is equal to X, so we get XN, and that tells us that NEX. Done. And the next one is, or not the next one, I'm going to leave one to you. So there's one in between, I think, called Festivo. It's an exercise for you. The last one is Barocco. It's a little bit trickier. MAN and MOX are the premises, and we're trying to get at NOX. Okay, so what do the premises tell us? The first one is that n equals nm, and the second one with the O here is x times 1 plus m does not equal 0. And we're trying to get a similar thing for x and 1 plus n. Okay, so the proof that I found, the simplest one I could find is this one. So we take x times 1 plus n times 1 plus m, and we look at that. And we expand the two terms here multiplied together. So that's 1 plus n plus m plus n times m. Okay, now we go from here to here. So the n times m is the same as n. Okay, so we could put an n here. And then we have an n here and an n here. Okay, we can commute, bring the n's together, and then n plus n is 0. So we just get 1 plus m here. And what do we know about x times 1 plus m? Well, our other premise tells us that's non-zero. Okay, that's non-zero, then we go back to the original thing, and we can conclude that this factor, x times 1 plus n, is also non-zero. And that's NOX. So this is great fun. And in our next video, we're going to look at the third figure ones. So it turns out that when we look at the third figure ones, which we haven't talked about yet, but it'll be interesting to have a look at them, there's a little bit of a complication. There's a little bit of an extra complication, and this was appreciated by Aristotle and subsequent logicians. So we're going to be able to see that complication exhibiting itself purely algebraically. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.